Large language models don't understand text the way humans do. They don't read sentences, recognize meaning, or understand intent. Instead, they rely on mathematical representations called embeddings, and specialized systems known as vector databases. In this video, we'll clearly explain what embeddings are, how vector databases work, and why they are a critical foundation of modern generative AI systems like Retrieval-Augmented Generation, or RAG. Let's start with the core problem. Computers fundamentally do not understand language. To a machine, text is just a sequence of characters with no inherent meaning. If you ask a computer to compare two sentences, it cannot determine whether they mean the same thing unless we first convert language into a format that machines can process mathematically. This challenge is at the heart of natural language processing and generative AI. This is where embeddings come in. An embedding is a numerical representation of text that captures its semantic meaning. In simple terms, embeddings convert words, sentences, or documents into long lists of numbers called vectors. These vectors encode meaning in such a way that similar pieces of text produce vectors that are mathematically close to each other. Embeddings allow machines to reason about language using mathematics instead of words. Why does this numerical representation matter? Once text is converted into vectors, we can compare meanings using distance and similarity calculations. Text that talks about the same concept ends up close together in vector space, even if the wording is different. Text that is unrelated ends up far apart. This ability to measure meaning mathematically enables semantic search, recommendation systems, and intelligent retrieval. Let's look at a simple example. The phrases, AWS Cloud Services, and Amazon Cloud Platform, have very similar meanings. When converted into embeddings, their vectors appear very close together. On the other hand, an unrelated phrase like, weather forecast today, produces a vector that is far away. This is how machines understand similarity without matching exact keywords. Now that we understand embeddings, the next question is, where do we store them? A vector database is a specialized database designed to store embeddings and efficiently search through them. Traditional databases are optimized for exact matches. Vector databases are optimized for similarity search across high-dimensional vectors. They allow GenAI systems to retrieve the most relevant information based on meaning, not keywords. Here's how vector search works step by step. First, a user submits a query. That query is converted into an embedding using the same embedding model used for stored data. The vector database then compares this query embedding against stored vectors using similarity algorithms like cosine similarity or inner product. The closest matches are returned in milliseconds, even across millions of vectors. Vector databases are critical for modern generative AI systems. They enable semantic search instead of keyword search. They allow large language models to retrieve relevant context efficiently, and they make it possible to scale GenAI applications to enterprise-sized datasets. Without vector databases, GenAI systems would be slow, inaccurate, and difficult to scale. In retrieval-augmented generation, vector databases play a central role. Documents are first converted into embeddings and stored in a vector database. When a user asks a question, relevant documents are retrieved based on semantic similarity. This retrieved context is then passed to the large language model, which generates an accurate and grounded response. This approach dramatically reduces hallucinations and improves reliability. Several vector databases are commonly used today. Amazon OpenSearch provides vector search capabilities integrated with AWS services. Pinecone is a fully managed vector database optimized for scale. Weaviate offers open-source flexibility with strong GenAI integrations. FAISS is a popular library for high-performance similarity search. Each option has different trade-offs depending on scale, cost, and architecture. To summarize, embeddings convert language into numerical representations that capture meaning. Vector databases store and search these embeddings efficiently at scale. Together, they form the backbone of modern generative AI architectures such as retrieval-augmented generation. In the next video, we'll compare RAG with fine-tuning and explain when each approach makes sense. If you're preparing for AWS or learning GenAI architectures, Check the link in the description for free practice resources. Thanks for watching.